our next and final speaker for the day. No pressure on knocking it out of the park to leave people on a good note. He has an evil twin lurking around somewhere. Everyone, please welcome the good twin, Zach.
My name is Zach. I work at MITRE. I'm going to be talking about preparing for the future, how climate change can affect food growth. So this is part of an old project called ORAC, which is Anticipatory Understanding Resilient Agriculture to Climate. This project was pretty wide scope in nature. It had about, I think, 12 people on it. In general, the idea is climate change can lead to changes in food growth can lead to those changes can lead to food insecurity, and then food insecurity can lead to violent conflict. So the whole project itself was basically, how do we understand what kind of changes climate change might cause that could lead to global conflict? This included a variety of things, including like identifying wheat fields using remote sensing, predicting crop production under various climate scenarios, modeling grain distribution to different areas and regions and locations, suggesting courses of action to improve food insecurity. And it actually resulted in a nice dashboard, which was great. And you could like visualize all these things, and it was really cool. I'm only going to talk about a little bit of that today, because this isn't a conference about R, and that's the statistics portion of it. So which is predicting crop production under various climate scenarios and determining what weather patterns are associated with increased crop simulation error in France. So as Jared said this morning, this is like an R and friends group. So today our friends are Python and our friends are GIS. So we used WOFAST, which is a crop growth model. It stands for, I think, World Food Studies. You can Google it online, it's open source. And that was wrapped in Python. And the idea was we want to simulate crop production in France, compare that to ground truth, understand where did like the WOFAST model get it wrong and why did the model get it wrong, and basically associate changes in climate to changes in food production. So here's a little bit of detail on PCSC and WOFAST. Like this just generates crop production, different geographic areas. Models run for each grid cell. You get the crop yield, you multiply it by the overall area of the region, and you get total crop for that region. Pretty straightforward. For weather data, we used the NASA Power API, which is also built into PCSC and used Python. And this gives us like a whole bunch of weather inputs: temperature, rain, sunlight, I think humidity, dew point, other things, which were all fed into the crop simulation model to generate crop production output. This only gives us historical data, and that's all we're going to talk about today, because this was just a historical analysis on how weather could affect food growth. The idea, though, was to use this for the future, and so MarkSim was a weather production option we identified as giving like decent, reliable future weather estimates, and that also would give a lot of variables for PCSE. So this is just for the general project. We do have like an idea of future weather production software that could be used. So this is really the more technical portion of the talk, and that's like the next few slides. But the idea was we want to understand, how does WOFAST project crop production trends, and like can it be used reliably into the future? The way we assessed like how reliable is it for the future is understandably to use it for the past. And so we ended up building a regression model, actually a few different regression models, that like basically build out a relationship between historical weather patterns over 20 years in France and the WOFAST crop production model. This regression model is built at 2 different levels of geography. France is broken into regions, which there are like 13 or 14 regions, and about 93 departments. And so we have analysis for both at the region level and at the department level, and basically to identify what kind of weather patterns are associated with what kinds of errors. Okay, so to recap our data sources, we have weather from the NASA Power API, we have crop production from PCSC and WOFAST. We use Winter Wheat 104. That was part of a preliminary analysis to try to figure out like which wheat strain could be reliably used for this analysis. Winter Wheat 104 was a good option. We have ground truth data from France, which is really critical for this whole study. We use soil depth because understandably how much wheat grows and how reliably it grows depends a lot on the soil and the land in which you plant it. And we used a 20-year analysis. So this is 2019, omitting 2016. We omit 2016 because it's just really an outlier year. And one of the themes of this talk is going to be like, how do outliers change things? In 2016, I think basically all of the France crop projection models got it wrong in terms of how much wheat was produced. So we omit 2016 from everything you see going forward. But the analysis itself is still, 19 years, which feels pretty good. Okay. To build this regression model, we used functional data analysis. And if you're not like stat savvy, maybe you haven't heard of it. And if you are stat savvy, you still maybe haven't heard of it. It's a very niche area. But in functional data analysis, your data themselves are represented by curves instead of like points. A classic example, and it's in this plot, is temperature data. So in this plot on the left, you have raw temperature data at 35 Canadian weather stations, and just the averages are plotted. But the goal of this graph is to show you that temperature itself is continuous, right? It's not like someone's height or weight, which are like basically stay the same or can be summarized in a scalar value. Temperature itself is a function, and what we're interested in is understanding what about these temperature functions and what about the sunlight functions and the precipitation functions? What kind of changes in yearly weather are associated with changes in crop production? So this analysis is going to have functional data in it. It'll be a little bit technical here. This is the most technical slide. I apologize for the integrals. I just thought they were helpful. But so in functional data analysis, either your response variable, your predictor variable, or both are functions. So here, our response variable is just percent error. For every year we simulated how much crop is being produced. We compared it to the ground truth. We computed percent error. We have that for all 19 years. We have that for every single region, every single department in France. This is a longitudinal model. And so we use data from over 20 years, scalar, the percent error. Our functions here are temperature, precipitation, and sunlight, since those are the three main ingredients that go into producing crops in agriculture. And this is using the LPFR function and the refund package in R. So a nice shout out to the refund package. It's regression for functional data. They actually make this all a lot easier than it really should be because it's complicated math. And at the bottom, for those of you who are interested in, this is the regression formula. Alpha I is a different intercept for every different region. Basically, it says we want to account for the fact that different regions in France are a little bit different. And so for each of those, we'll fit one model, but we'll give them each different intercepts. And we use temperature, precipitation, and irradiance, which is sunlight, for every year and every region. And we compute percent error and kind of see how do these two correlate, or not correlate, but how are they associated with each other. So this was an interesting finding, we thought, which was at the regional level, so at the level of 13 regions in France, if you regress the error in crop production on just those three covariates, you get a pretty decent model. Your adjusted R squared is 0.68, which I know there's an R squared talk coming up. It basically 68% of the error can be explained by changes in rain and sunlight, which I thought was really interesting because it's saying that the simulation models themselves are pretty good, except when the weather changes them. And so what changes in weather are causing our crop production models to be wrong or to be off more than we thought? And those are changes in rain and sunlight. AIC also lower is better. The rain and sunlight model for this regional model that was the lowest for rain and sunlight. And so just the key takeaway is rain and sunlight are important factors to consider when understanding low-cost error. The other thing to note about the slide is you can't really see it, but this image was made in GIS. GIS is our friend. The colors on behind France, really behind Spain and the other countries, those indicate soil depth. And so pink is very low soil depth. So we excluded those three regions in red, which had a lot of low soil depth regions. Those also aren't really large producers of wheat. And so it wasn't so critical to include them. But excluding those from the analysis and also the island really improved the results. In general, this kind of modeling is a little bit sensitive to outliers, and I'll show that in more detail soon. But this by itself, I thought was actually pretty good. I was not expecting an R squared of 68 or 0.68. Okay. We also wanted to validate this at the department level to kind of see what does this look like on a more granular scale. And so this was a three-step process. First is we exclude the departments from the regions that we excluded also to kind of keep it apples to apples-ish. We removed 2 more, which had really bad outliers. And then we also removed a bunch more, which were also bad outliers. And I'm not advocating as like removal of outliers as a data analysis method. That would be insincere and wrong. But I do want to say sometimes it's okay to remove outliers kind of as an exploratory phase or to gain an understanding of the data set. So that's what we did here. So you can see this is pretty much the same regression minus, I guess, 1 department here at the regional level, but now it's at the department level. At the department level, we have a lot more granular data. We have more regions with outliers, and this map itself, the results are not as good. Like 12% R squared is nowhere near as good as 0.68. Because we're using a mixed effects model, we can do some fun outlier comparisons. And what's going on here is that we have at least 2 outliers, 2 outlying departments that are really screwing everything up. Like everything else, the residuals are pretty good. They mean 0. Their outliers aren't so bad. But here, everything is just kind of way out there. So out of curiosity, we kind of removed those, saw like how good would it look without those. And it looked a little bit better, honestly, but it still was really not so great. Now it's rain, temperature, and sunlight that have the best R squared, but 0.16 is still nowhere near as good as 0.68. So we keep going. And now we have the 71 departments over 19 years. And you can see once we took out those 2, there was still a bunch of outlier years up here. Those also kind of cause a bunch of issues. To do this analysis again, we maybe would have taken out just the individual years that were problematic for those departments. But we just took out all the departments because that was easier to do in a data sense. And now everything looks beautiful, with the exception of the fact that like we took out maybe a third of the departments in France. But at least the results look better. And so like I don't want to say like, oh, remove outliers, everything gets better. I do want to say remove outliers, and maybe you'll get an understanding of what's going on in these other places. And identifying outliers is important. I think the regional level regression was actually pretty solid, 0.68, taking out low soil depth. This is much more cherry picky, and cherry picking is like really not healthy and not something we should advocate for. But it's kind of good to know that there are just these few departments in France that are really messing everything up. And when you look at the big breadbasket regions, which is what we're interested in, like in particular on the map, the darker regions produce more wheat. And you can see like we're including most of the darker regions on the map. Then we actually get a model that really explains what errors are happening in the crop production simulation. Okay, and when you look at the residuals here, they have, certainly look really good. And this is what things should look like, things centered around 0, no terrible outliers every which way. So like, in short, we wanted to see, could WOFAS be used to predict future crop production trends? And we showed that rain and sunlight are the key weather factors, at least in this model, in this regression of explaining historical error in the crop production. One other thing about functional data analysis, which I didn't include in these slides for a number of reasons, is you can actually see like when in the year things are bad, or not things are bad, but not only is like, if you do a traditional regression, you would like take average sunlight, take average rain, take average temperature, and just use those. But when you include the whole data from the whole year, you can say like, okay, from January to August, we care more about temperature. And in the spring, we care more about changes in rain. So it really helps narrow down the analysis in terms of what times during the year and what weather factors during the year are more responsible for causing issues in crop production. Okay. And so if you were to do this kind of crop production modeling again, you need a representative crop strain and model. We used winter wheat 104. We used good weather data from NASA Power API. The soil depth map helped us figure out what regions in France don't really grow wheat and which ones should we not really care so much about because we're more interested in the bread baskets. And unit valid simulator, which we have in PCSA and WOFAST, and also MarkSim moving forward. Actually the last talk, and that's 5 minutes early. So this was funded by MITRE's Independent Research and Development Program. I have an email address. I also have a Twitter account. You're welcome. And I have a LinkedIn, which is under my name. You're welcome to reach out for any of those, if you're interested in any of those things. Okay. Thank you, guys.